Good morning, dear students, and welcome back to our course. In the last lecture, we discussed in detail about the concept of mathematical modeling of a control system. So, till date, so far in this particular course, we discussed in detail about the fundamental aspect of what exactly the system is. So, how you can define system. So, basically, system is nothing but a combination of different physical components which entirely act as a unit in order to achieve some objective. And if you add control word in the system, that means the system is capable to perform three functions simultaneously. First one is called as direction, second one is called as regulation, and third one is called as commanding. That means if a design system is capable to perform direction, to perform regulation, to perform commanding operation, that means the system, if it is capable to perform direction, if it is capable to perform regulation, and if it is capable to perform commanding operation on itself or some other component of the system, then we can treat that particular system as a control system. Then we discussed in detail about the concept of plant and controller. So what is plant? Plant is nothing but the portion of a system whose function is to be controlled. And what is controller? Controller is nothing but the element of a system which may be present inside the system, which may not be present inside the system, but its main function is to control the action of the plant. So that element is nothing but controller. And to understand the concept of plant and controller, we have taken a very simple electrical circuit where we have a supply voltage, and to this we have connected a switch, and then somewhere over here we have connected a bulb which is in the form of load. So here this is nothing but source, which is nothing but excitation to this particular system. Then here we have a switch, and then here we have a lamp. Now by changing the position of the switch, we are in a position to control the state of lamp. We can turn on the lamp, we can turn off the lamp. So with respect to this particular circuit, here the switch is also known as controller, and lamp is also known as plant. Why? Because plant is the portion of a system whose function is to be controlled, and here the function of this plant, that is nothing but lamp or bulb, we are going to control through this switch, which is also called as the controller. Then we discussed in detail about the concept of disturbed signal. What is disturbed signal? How they are created in the system? There are basically two different domain through which we can have disturbed signal in a given system, maybe due to internal source and maybe due to external source. So they are classified into two main category. First one is called as internal disturbances, and second one is called as external disturbances. And then we discussed in detail about the classification of control system. That is very important, how to classify control system. For example, as far as gate syllabus is concerned, the three most important type of control systems are nothing but, first one is called as time variant, and second one is called as time invariant control system. Then second objective to classify control system is linear and non-linear type control system. And third one is open loop and closed loop type control system. That is again very important. Now What is time variant and what is time invariant control system? I told you that this variancy we are going to define in terms of system parameter, whether the system parameter is going to depend or vary with respect to time or not. For example, in case of time variant control system, the parameter of the system is a function of time. That means P of t. Even though the input and output are not the function of time. So those type of systems are called as time variant. What is time invariant? Time invariant is nothing but a type of a control system in which the system parameters are not the function of time. That is important. Even though the input and the output of the systems are a function of time. That is important. That means the best example is series RLC circuit, where once we have designed the circuit, the value of resistor, the value of inductor, and the value of capacitors are almost going to be constant. Even though if you design the circuit at this moment, or if you design the circuit and check the value of RLC after 1 day, 2 day, or even after 1 year, the value of R, the value of L, and the value of C are almost going to be the same. That means their values are not going to change with respect to time. Even though the input applied to the circuit and the output which is going to be appear across each element in the form of voltage, maybe here is V R of t, here we are having VL of t, and here we are having VC of t. All are nothing but the function of time. So these type of systems are called as time invariant control system. And I told you that by default, to have a ease of calculations, we consider the system as time invariant. That means the system parameters are not going to vary with respect to time. That is very important. Then we discuss the concept of linear and non-linear control system. So what is linear control system? A system is said to be linear if it is going to obey the principle of superposition. That means if it is going to follow superposition principle, then we can treat that particular system as linear. Otherwise, the system is going to be non-linear. Then we discuss in detail about what is the meaning of this superposition principle and how to identify that whether a system is capable to follow this superposition principle or not. And finally, we conclude that a system is said to be linear if it is going to follow superposition principle. That means it has to follow two properties simultaneously. First one is called as additive property, and second one is called as homogeneous property or homogeneity property. So how to define additive property? Additive property means what? If you have a system, and to that system if you apply some input, say x1, corresponding to that the system is going to generate some output, say y1. Now to the same system if you apply input, say x2, it is going to generate some output, say y2. Now what we need to do, now to the same system we are going to provide the collective action of these two input like x1 plus x2, and we are trying to observe that what is the output produced by the system in this case. If the output is going to be the addition of y1 and y2, then we can treat this particular system as additive property system. That means the system is going to follow additive property. In the same way, uh, about non-linear, sorry, in the same way about homogeneous, what we need to do. Suppose if you have a system, and to that system if you applied some input in the form of x, corresponding to that it is going to generate some output, say y. Now, what we need to do, if you manipulate the input signal by a factor of, say, A, the same factor has to be appeared on the output side. That means if the input is varied by a factor A, and due to which the output is again going to vary by the same factor, then we can treat this particular system as homogeneity. Hence, if the system is capable to obey both the properties simultaneously, that means it is additive as well as homogeneous, then we can treat that particular system is following the principle of superposition. Hence we can treat the system as a linear system. Otherwise the system is going to be a non-linear one. And then we discussed in detail about the concept of open loop and closed loop control system. So what is open loop control system? So in case of open loop control system, suppose this is nothing but a system, or let me write this as system. Suppose this is a system, and to this system we applied some input in the form of excitation, say R of t, and corresponding to that it is going to generate some output, say C of t. Now, in case of open loop control system, output depends on input, but input does not depends on output or change in output. So that type of systems are called as open loop control system. Whereas, what do you mean by closed loop control system? The closed loop control system means where we have a concept of feedback. So what we need to do? So we can make open loop system as closed loop. The thing is that here we need to add a summing point, and to this we need to add a reference input signal, that is R of t, and here we need to have a feedback path. So here we are going to have a feedback element like this, and the feedback element here we need to take feedback element, and it is going to generate some signal. That signals are nothing but say B of t, feedback signal. It may be plus, it may be minus, that depends upon the nature of feedback path. That means whether we are going to take positive feedback signal or negative feedback signal, and based on that it is going to generate error signal, which is nothing but E of t. So here I can write E of t as R of t plus minus B of t. This is very important. And if you open this particular system, again here we are having two main components in it. First one is called as the the controller, and then we have the plant. So I can write here as, here we are going to have a controller followed by, somewhere over here we are going to have a plant. So the output of this summer, which is nothing but error signal, is provided as an input to the controller, and it is going to generate some actuating signal which is provided as an input to the plant, and then is going to generate the controlled output, which is nothing but C of t. And the value of this uh, actuating signal which is produced by the controller is in such a way that the error has to be zero. That is our final main objective. That is very important. This is what the concept of open loop and closed loop control system, and then we discussed the advantages, disadvantages, and some practical examples of open loop and closed loop control system. Once we have done with this, we started how to find out the mathematical modeling of control system. So basically, mathematical modeling is nothing but what? It is a process of representing a system through some set of mathematical equations. For example, if you have a system, and suppose if you want to represent this particular system through some sets of mathematical equation, so these equations are nothing but the mathematical modeling of this particular system. It is not at all necessary that the systems are always going to be linear, or you can say differential equation. It may be integral differential equations or something like that. The thing is that through those sets of mathematical equations we are in a position to define the behavior of the system. That means वो system draw करना क्या, या उसके against में वो mathematical set of equation लिखना क्या, एक ही बात है. So that concept is nothing but mathematical modeling. So there are n number of ways to represent a system. We may represent the system in the form of block diagram. We may represent the system in the form of signal flow graph. We may represent the system in the form of transfer function. We may represent the system through sets of mathematical equations. But ultimately, the overall objective is, through each and every representations we are trying to define the behavior of the system. In the same way, in case of mathematical modeling, again we are trying to represent the behavior of a system, maybe it's a static or maybe it's a dynamic, through these sets of mathematical equation. So that process is called as mathematical modeling. And then depending upon the nature of system, that means what kind of systems we are having with us, based on that we can define or classify the mathematical modeling into two main domain. First one is called as mathematical modeling of electrical system, and second one is called as mathematical modeling for mechanical system. Again, as far as electrical systems are concerned, first of all, we should know that what are the basic fundamental components which plays an important role to define or to design any electrical system. And the answer for this is nothing but resistor, then we have inductor, then we have capacitor, followed by we have voltage, current, flux, charges. So these are some important fundamental operating parameters through which we can easily define the behavior of electrical system. In the same way, as far as mechanical systems are concerned, depending upon the nature of displacements, whether we are having linear or whether we are having non-linear, we can further classify the mechanical systems into two main domain. First one is called as translatory motion type mechanical system, and second one is called as rotational motion type mechanical system. Then we discuss that what are the fundamental operating parameters in case of translatory motion type mechanical system. And the answer for this is, in case of translatory motion type mechanical system, here we have mass. Let me erase this. So in case of translatory motion type mechanical system, we have mass indicated by symbol m. Then we have force indicated by symbol F. Then here we have damping coefficient indicated by symbol B. Then spring constant indicated by symbol K. Then here we have linear velocity indicated by symbol X. And we have non, you can say, linear. This is nothing but linear displacement indicated by symbol X. And then we have linear velocity indicated by symbol V, which is going to be equals to dx by dt. So you have to correct this. This x is not linear velocity, it is linear displacement. In the same way, in case of rotational motion type mechanical system, instead of having mass, here we are having inertia indicated by symbol J. Then instead of force, here we are having torque indicated by symbol T. Then damping coefficient remain as it is, spring constant remain as it is. Then instead of having linear displacement, now here we are having angular displacement denoted by symbol theta. And then linear velocity, we are having angular velocity indicated by symbol omega, and this is going to be equals to d theta by dt. And then we discussed the fundamental equations of force and torque corresponding to the three main components which are essential to define any mechanical system. Like in case of translatory motion type mechanical system, we have mass. So how to represent the force contribution of mass? So it is indicated by symbol Fm, and it is going to be equals to what? M d2x by dt square. In the same way, force contribution due to damping coefficient, or you can say friction coefficient, is indicated by symbol Fb, and it is going to be equals to b times dx by dt. In the same way, force contribution due to spring constant k, it is indicated by symbol Fk, and it is going to be equals to k times of x. In the same way, if you are interested to find out or represent the torque coefficient or torque component due to inertia, it is indicated by symbol Tj, and it is going to be equals to what? J d2 theta by dt square. In the same way, torque coefficients due to damping is nothing but b times d theta by dt. And finally, the torque contribution due to spring constant k is nothing but k times of theta. This is very, very important. And finally, in order to find out the mathematical modeling of a mechanical system, we need to apply the concept that at equilibrium condition, the input force is going to be equals to the output force. That means what is the force you have applied, that is going to be equals to the force that is going to be appear across the fundamental elements available in that mechanical system, like force contribution due to mass plus force contribution due to damping coefficient plus force contribution due to spring constant. In the same way, you can rewrite the equation at equilibrium condition corresponding to torque, and this is nothing but input torque is going to be equals to torque contribution due to inertia plus torque contribution due to damping coefficient plus torque contribution due to spring constant. This is again going to be very important. So these points we have discussed in the last lecture, and in today's class we need to discuss one of the most important topic from control system that deals with the concept of transfer function. Transfer function. So in this particular lecture, our objective is to understand what is transfer function and why transfer function plays an important role in order to analyze the behavior of a given system. So first we will discuss in detail about what exactly transfer function is, what are the different types of techniques through which we can define transfer function, then what informations we can collect from transfer function, what is the general mathematical approach to represent transfer function for any physical system. Then we are going to discuss the fundamental properties of transfer function, and we are going to solve some previous year gate questions that are asked on transfer function. For example, if you know the system mathematical modeling, how to find transfer functions and all, or if you know the representation of system in the form of circuit diagram, how to find the transfer function for that particular system. So let us begin with our today's session. So what is transfer function? First definition or first technique to define transfer function is nothing but it is nothing but a parametric function. Parametric function of a system which only depends on system parameter, which only depends on system parameter. System parameter. So this is the first definition of transfer function. So what is transfer function? It is nothing but a parametric function of a system whose value only depends on system parameter. That means once the system is designed, once the parameters are fixed, the corresponding transfer function of that particular system is going to be fixed. It does not depends on which type of input you have applied to that particular system and what response you are getting as an output. So transfer function is nothing but a parametric function of a system which only depends on system parameter. It does not depends on input and output of that particular system. Then second way to define transfer function is nothing but, and which is commonly used by the student, is nothing but transfer function is defined as the ratio of Laplace transform of output to Laplace transform of input by assuming all initial conditions. This is very important. Initial conditions to be zero. This is another way to define transfer function. And what is that? It is nothing but the ratio of Laplace transform of output to Laplace transform of input by assuming all initial conditions to be zero. This is very important. And in control system, in most of the time, we always define transfer function through this definition only. That means if you have a system and your objective is to find out its transfer function, so what we need to do, we need to take the Laplace transform of output, we need to take the Laplace transform of input, and finally we need to take the ratios of these two quantity by assuming all initial conditions to be zero. So whatever the parametric function you are getting as an output, that itself define the transfer function of that particular system. This is second definition to uh, define what exactly transfer function is. Let me elaborate this particular term. That means ratio of Laplace transform output by Laplace transform of input, assuming all initial conditions to be zero. So let us consider that we are having a system, and This system is designed through some parameters. So here we are having a parametric function, or you can write here we are having a system parameter indicated by symbol p of t. And to this system we apply some input in the form of excitation. Let us consider that it is going to be r of t, and corresponding to that the system is going to generate some controlled output in the form of response. Let us consider that it is going to be small c of t. So p of t indicate the parametric function of the system, and here r of t is nothing but the input to the system, and c of t is nothing but the output generated by the system. Now suppose we are interested to find out the relationship between output, input and this parametric function. So mathematically I can write here as output is nothing but the parametric function of the system times the input. So I can write here that this output is nothing but input times the parametric function. So the same thing is mentioned over here. Output is nothing but parametric function of system times the input. Now this output is nothing but C of t, which is going to be equal to parametric function of the system, which is nothing but P of t, or you can represent this particular function as G of t. Both are nothing but the same thing. So I can write here as g of t, where g of t indicate the parametric function of system multiplied by input, which is nothing but r of t. This is very, very important. That this will be your equation number 1. Now, again, I can redefine this particular system from time domain to frequency domain. And how to do that? I can convert this particular system from time domain to frequency domain by applying the concept of Laplace transform. That means if you take Laplace transform, the same system I can define as like this. So here we are going to have a system. Now instead of having g of t, I need to take here capital G of s, where capital G of s indicate the parametric function of the same system, but it is now represented in frequency domain instead of representing that in time domain. Then again we need to have some input r of t. Now this is going to be capital R of s. I already told you that in case of time domain we represent the quantity through small letters, but in frequency we need to represent them by capital letters. So same topology I have applied over here. So small g of t now we can represent as capital G of s. In the same way, small r of t now we can represent that through capital R of s, and somewhere over here we need to have capital C of S, where capital C of S indicate the response generated by the system in frequency domain. Now again we need to write the relationship between response, parametric function and input through the same mathematical equation which we have defined in the previous case. So I can write here as response, or you can say output, is going to be equal to parametric function of the system times the input, which is nothing but r of s. Now if you rearrange this particular term, I can write here as c of s divided by r of s is going to be equals to g of s. This is the mathematical formula to calculate transfer function of a system. Why? Because see, definition number 2, it is defined as the ratio of Laplace transform of output. Now what is C of S? C of S is nothing but Laplace transform of output, because output in time domain is C of t. If you apply Laplace transform to the C of t, it will become C of S. So C of S is nothing but Laplace transform of output divided by what is R of S. R of S is nothing but what? Laplace transform of input. That means if you have input like R of t, and if you apply Laplace transform, it is converted to R of S. So what is transfer function? So it is defined as the ratio of Laplace transform of output by Laplace transform of input. And while defining this parametric function, we assume all initial conditions, I can write here as IC, is nothing but what? 0. So here all initial conditions are nothing but 0. So hence this ratio of C of S by R of S is nothing but the transfer function for this particular system. So I can write here as transfer function is simply the ratio of C of S by R of S assuming all initial conditions to be 0. This is very important. So this is the very common definition which we normally use in order to define the concept of what? Transfer function. This is very, very important. Then the third way to define transfer function is nothing but, see here, what is C of S? C of S is nothing but what? Response, or you can say the output of the system, but in frequency domain. What is R of S? It is nothing but input, or you can say excitation of the system, but again it is in frequency domain. So ultimately, if you see transfer function, it is simply the ratio of output by input. And what is output by input? In electrical domain or in any physical system, the ratio of output to input is nothing but what? Efficiency, indicated by symbol eta. So another way to define transfer function is nothing but, it is nothing but the ratio of output by input, or you can say it is nothing but the efficiency of the system, but in frequency domain, because here output we have taken in frequency domain, input we have taken in again frequency domain. So I can write here as transfer function is nothing but a way to represent the efficiency of the system but in frequency domain, assuming all initial conditions to be 0. So this is third way or third terminology through which we can define the concept of transfer function. So transfer function is nothing but what? The efficiency of the system in frequency domain by assuming all initial conditions to be 0. Why it is efficiency? Because ultimately transfer function is nothing but what? It is the ratio of output by input, and the ratio of output by input is nothing but what? Efficiency. But here in this case we define output in frequency, we define input in frequency. That's why transfer function is nothing but what? A way to represent the efficiency of a system but in frequency domain, assuming all initial conditions to be 0. So this is the third way through which we can define the concept of what? Transfer function. So ultimately, from this particular lecture onwards, in the course of transfer function, we in the course of control system, we define transfer function as the ratio of Laplace transform of output to the Laplace transform of input by assuming all initial conditions to be 0. So we can define this as transfer function is nothing but C of S by R of S. This is very important. So this point you have to remember. So once you understood this, what exactly transfer function is, uh, let us try to understand what kind of informations we can get from transfer function. Number one, through transfer functions, we are in a position to find out the poles of system. Now, what is poles or what are poles? Poles are nothing but those complex frequency, where the magnitude of transfer function is going to be infinite. That is important. In the coming sessions, we are going to discuss in detail about what exactly pole is. But for time being, let us consider that through transfer functions, we are in a position to find out the poles of the system. Now, what are poles? Poles are those complex frequencies where the magnitude of transfer function is going to be infinite. In the same way, through transfer functions, we are in a position to find out the zeros of the system. Now, how to define zeros? Zeros are nothing but those complex frequencies where the magnitude of transfer function is going to be 0. That's why they are called as zeros of the system. Then the third information which we can collect from the transfer function is nothing but the overall gain of the system Then once you know the transfer function of the systems, we are in a position to find out what is the order of the system, and we are also going to find out what is the type of the system. So if you are interested to find out what is the order of the system, what is the type of the system, then we can easily find out these values or these factors corresponding to a given system if you know the transfer function of that particular system. That means the order of the system and type of the system. Then we can also find out the stability of the system. But to find out the stability, we need to apply some logic, we need to apply some laws, we need to apply some rule. But to find out the stability of a system through those laws or through those rules, maybe Hurwitz criteria, Bode plot, then root locus technique, Nyquist plot, polar plot. First and the fundamental aspect that is required is nothing but the transfer function of the system. That means if you know the transfer function of the system, maybe say open loop transfer function or say closed loop transfer function, then we can apply those concepts to find out its stability. So stability we can find out through these techniques once we know the transfer function of that particular system. That is very important. In the same way, we can also find out the time domain analysis and frequency domain analysis once we know the transfer function of the system. So time domain analysis and frequency domain analysis also we can find out. But to find out those things, again we need to have the transfer function of that particular system. So because we are in a position to find out all these things related to the system, if we know the transfer function of the system, that's why it is very essential for us to find out the transfer function of a given system. So basically we are in a position to find out what is the pole of the system. Poles are nothing but those complex frequencies where the magnitude of this transfer function is going to be infinite. Then we are in a position to find out the zeros of the system. Now what are zeros? Zeros are nothing but those complex frequencies where the magnitude transfer function is going to be 0. Then we are in a position to find out the overall gain of the system. And then through transfer functions, we are in a position to find out what is the order, what is the type of the system. Then we are also in a position to find out the stability, followed by time domain analysis and frequency domain analysis response of the system. That is important. Now let us try to discuss what is the general mathematical way of representing transfer function. For example, if you have a physical system, and suppose if you are interested to find out its transfer function, then what is the most general way of representing the transfer function for any given physical system that we will learn. So in this particular topic, our objective is to understand what is the mathematical representations corresponding to transfer function for any physical control system. So mathematically, we can define the transfer function like TF is going to be equal to an times s to the power n plus a n minus 1 s to the power n minus 1 plus a n minus 2 s to the power n minus 2 plus so on up to a n minus n, that is going to be a naught, s to the power n minus n, that is s to the power 0, that is going to be 1. So this will be the numerator portion of the transfer function, and then the denominator portion. So here denominator portions we are going to define like bm s to the power m plus bm minus 1 s to the power m minus 1 plus bm minus 2 s to the power m minus 2 plus so on. Finally we are going to have b naught. That is very important. Now suppose through this numerator and through this denominator, if we take some terms as a common, and the term which we are going to take common is nothing but an from the numerator and bm from the denominator. So I can rewrite this equation as, if you take an common, so it is going to be like Sn plus an minus 1 by an, then s to the power n minus 1 plus an minus 2 by an s to the power n minus 2 plus so on up to a naught by an whole divided by, here I'm going to take bm common. So this is going to be bm in bracket, this is going to be s to the power m, then plus, here we need to take bm minus 1 divided by bm s to the power m minus 1 plus bm minus 2 whole divided by bm s to the power m minus 2 plus, and so on up to here b naught by bm. That is again important. Now if you see this equation very carefully, here the ratio of this an by bm, here we can define this ratio like an by bm by another factor indicated by symbol k. So now instead of writing this an by bm, now I can write this equation as transfer function is going to be equal to k times this entire equation. So here this k is known as overall gain of the system. This is very important. So through transfer functions we are in a position to find out what will be the overall gain of the system. So this is what the expression for, or general mathematical representations of a transfer function for any physical system. Now I told you that through transfer functions we are in a position to find out the poles and the zeros of the system. So what is poles? Poles are nothing but what? Those complex frequencies where the magnitude of transfer function is going to be infinite. So in order to find out the poles, let me rewrite this equation like, this is going to be the numerator polynomial function, this is going to be numerator polynomial function, and this is going to be denominator polynomial function. So numerator polynomial function is this entire term, and denominator polynomial function is going to be this entire term. So ultimately transfer function is nothing but the ratio of numerator polynomial function which is defined in complex frequency, or which is defined in frequency domain, to the uh, denominator polynomial function, again it is going to be defined in frequency domain. So nr by dr is nothing but tf. Now what is the concept of pole and what is the concept of zero? So poles and zeros. Now what are poles? Poles are nothing but those complex frequency where the magnitude of this transfer function is going to be equals to what? Infinite. And to find the value of poles, what we need to do, we need to equate denominator polynomial function of transfer function to 0. That means if you equate this particular term to 0, and if you try to find out the value of s, or you can say the roots of this particular equation, because this equation is defined in terms of frequency, complex frequency, therefore you will get the value of S1, S2, S3, and so on. So these values of S1, S2, S3 are nothing but those complex frequencies where if you try to find out the magnitude of transfer function, it is going to be infinite. So these complex frequencies are known as poles of the system. In the same way, suppose if you are interested to find out the zeros of the system. So zeros are nothing but those complex frequencies where the magnitude of transfer function is going to be what? 0. That means to find out the value of 0, what we need to do, we need to equate the numerator polynomial function of transfer function to 0, and we need to find out the value of complex frequency like S1, S2, and so on up to Sn. Now these complex frequencies are nothing but zeros. Why? Because at these complex frequencies, if you try to find out the magnitude of transfer function, it is going to be 0. So thumb rule is that in order to find the values of pole, what we need to do, the denominator polynomial function of the transfer function we need to equate to 0 and find out the values of complex frequencies. Those complex frequencies are nothing but poles of the system. In the same way, in order to find out the zeros of the system, what we need to do, we need to equate the numerator polynomial function of the transfer function to 0 and find out the values of complex frequency. Those complex frequencies are nothing but a kind of frequencies where the magnitude of transfer function is going to be 0. That's why they are called as zeros of the transfer function. So I hope this point is clear to everyone, how to find poles and how to find zeros. To find poles, equate denominator polynomial function to 0, and to find zeros, equate numerator polynomial function to 0. That is important. Now for any physical system, this is very important. For any physical system, there is a relationship between this m and this n. And what is that relation? The value of m is always going to be equal to or at the max greater than or at the max equal to n. This is very important. For any physical system, the value of m is always more than or at least it is going to be equal to n. That means m indicate how many number of poles are there, n indicate how many number of zeros are there. For any physical system, the number of poles are always going to be more than or at the max equals to the number of zeros. This is very important. For any physical system, you take any physical system, and if you try to apply the concept of transfer function, find out its transfer function, and then find out how many number of poles are there, how many number of zeros are there. Poles are always going to be more than zeros, or the worst condition is that poles and zeros are always going to be equal if it is a physical system. If it is not a physical system, then in that case hypothetically you can take that zeros are more than pole, but practically no physical system is going to obey this particular equation. The thing is that if you have a system that is physically existed, then in that case the number of poles are always more than zeros, or at the max number of poles and zeros are going to be equal. So this term you have to remember, that m is always more than n, or at least it is going to be equal to n. Reverse condition is not possible. That means n is more than n. This condition never going to be happen. That means number of zeros are always going to be less than number of pole, or at the max they are going to be equal. This point you have to remember. So uh, I hope this point is clear to everyone, what exactly pole is, what exactly zero is, how to find pole and how to find zeros from the transfer function. So in order to find the value of pole, what we need to do, poles are nothing but those complex frequencies where the magnitude of transfer function is going to be infinite. And what are zeros? Zeros are those complex frequencies where the magnitude of transfer function is going to be 0. And the relationship between number of poles and number of zeros are nothing but if you take any physical system, the number of poles are always going to be at least equal to number of zeros, or they are always more than number of zeros. That is very important. Now let us try to discuss what are the properties of transfer function. So properties of transfer function. Number one property. It is the ratio of two polynomial in S domain. It is the ratio of two polynomials in S domain, or you can say in frequency domain. I hope this point is clear to everyone, because we define the concept of transfer function by taking this particular topology. That means transfer function is defined as the ratio of Laplace transform output by Laplace transform input by assuming all initial conditions to be zero. That is important. So basically, transfer function is nothing but the ratio of two polynomial functions, that too in S domain or in frequency domain. Then second property of transfer function is that it is a parametric function of the system. It is a parametric function of the system. That means it only depends on system parameter. It does not depends on input and output of the system. This is the second property of transfer function. Third property is that while defining transfer function, we assume all initial conditions to be zero. That is very important. That means through transfer function technique approach, we are not in a position to identify how the initial conditions of the systems are going to affect the performance of the system. Why? Because while defining transfer function, we assume that all initial conditions are nothing but zero. So that you have to remember. And then point number 4 is that in case of any physical system, if you take any physical system, the number of poles are always more than number of zeros, or at the max they are nothing but equal. So this is very important. This property you have to remember, that if you take any physical system, the number of poles are always going to be more than number of zeros, or at the max they are going to be equal. But the reverse situation is not possible. And fifth property of transfer function is that it is applicable to linear time invariant system only. That means if you have a linear system, that if you have a time invariant system, then it is very easy to find out its transfer function. So these are some 5 fundamental properties of transfer function that you have to remember. First property is it is the ratio of two polynomial in frequency domain or in S domain. Second thing is that it is the parametric function of the system. That means it only depends on system parameter. It does not depends on input and output of the system. Then third is, while defining transfer function, we assume all initial conditions to be zero. Fourth is, for any physical system, the number of poles are always greater than, or at the least they are going to be equal to zeros. But the situation of opposite sense is not applicable. That means zeros are more than poles. This is not possible for physical system. And fifth point is, it is applicable to linear time invariant topology only. This is very important. Now, once we have done with this, once we understood what exactly transfer function is, what is the importance of transfer function, why we need to go for transfer function, because through transfer functions we are in a position to find out the poles, the zeros, then we are also in a position to define the system stability. Also, we are in a position to find out the order, the type of the system, and then we are also in a position to check whether the system is stable or you can say unstable. So let us try to solve some numerical on transfer functions topology. That means if you have a system, maybe in the form of mathematical modeling, maybe in the form of some physical representations, how to find out its corresponding transfer function. Okay, so the first numerical that we need to solve is like this. Here our objective is to find out the transfer function of a system whose mathematical modeling is directly given to us. That means we have a physical system which is represented by the following differential equation, and the differential equation is d2 c of t by dt square, then plus 10 d c of t by dt, then plus 5 c of t. It is going to be equals to what? 7 dr of t by dt, then plus r of t, where this c of t is nothing but the controlled output, controlled output, and this r of t is nothing but the reference input of the system. And here our objective is to find its transfer function, and the system is given in the form of mathematical modeling. So this equation define the behavior of the system. Hence, this indicate the mathematical modeling for the system. And here this C of t indicate the output and R of t indicate the input. And our objective is to find its transfer function. So I told you that transfer function is nothing but what? The efficiency of the system in frequency domain. That means we need to find out the ratio of C of S by R of S by assuming all initial conditions to be 0. So here the mathematical modeling of the system is given in time domain, and we need to convert this from time domain to frequency domain, and this is possible only when we apply the concept of what? Laplace transform. So how to solve this numerical? The solution for the numerical is like this. First of all, we need to apply the concept of Laplace transform in order to convert this entire system or entire mathematical modeling from time domain to frequency domain by assuming all initial conditions to be 0. So if you apply this particular logic, we can find out the representation of the system from time domain to frequency domain. So d2 c of t by dt square, this we can write like in frequency domain. So this is going to be equals to what? S square times c of s. I hope this is clear to everyone, because here we have assumed that all initial conditions to be 0. So s, then here we need to take c of 0, then c dash of 0, and all initial conditions are nothing but 0. So c of 0 and c dash of 0 are nothing but 0. That's why straight away we can take this as s square c of s, then plus, here we need to take 10. Then if you apply Laplace transform to this, Laplace transform of dc of t by dt, so it is going to be equals to what? S c of s, then plus 5 Laplace transform of the c of t is going to be equals to what? C of s. This is going to be equal to 7 times Laplace transform of this d r of t by dt. So it is going to be equals to what? S into capital R of S, plus Laplace transform this R of t is going to be R of S. I hope this is very clear to everyone. Here we simply apply the property of Laplace transform to convert the function from time domain to frequency domain. And the important thing is that we have assumed that all initial conditions are nothing but 0. That's why the remaining terms of these expressions we have taken as 0. So in this case we are having c of s, c dash of s, but all are nothing but 0. Now in this equation, if you take this c of s common, so how we can write this? If you take c of s common, I can write this equation as s square plus 10s plus 5. This is going to be equal to, from this equation we are going to take r of s as common. So if you take r of s common, so it is going to be 7s plus 1. Now what is transfer function? It is nothing but the ratio of Laplace of output by Laplace of input. So here we are having output. Now what we need to do? We need to shift this input from this particular side to this side, and this entire term we are going to shift on this side. So I can write here as transfer function for the system, which is nothing but C of s by R of s is going to be equal to 7s plus 1 whole divided by s square plus 10s plus 5. I hope this is clear to everyone. So this is the way we can find out the transfer function for this particular system whose mathematical equation in the form of differential equation is known to us. The thing is that first we know the mathematical modeling, or we must know the uh, representation of system, maybe in physical form, maybe in the form of some set of mathematical equation. Then we need to apply the concept of Laplace transform to convert that from time domain to frequency domain, and then we need to take the ratio of output by input. Once you have taken the ratio of output by input by assuming all initial conditions to be zero, so whatever the terms you are having in the form of frequency components, that expression is known as the transfer function for this particular system. Today we will stop at this particular point. In the next lecture, we will continue through the same numerical. We are also trying to find out what is the poles and what are the zeros for this particular system, and how to represent these poles and zeros in the pole zero diagram, or you can say in S plane of the system, that we will learn in the next lecture. Also, we are going to solve some more numerical on transfer function approach. Thank you.